So next up on our list of useful alkyne reactions is the dihalogenation. And for the moment, we'll stick to Br2. Um, Here, much like the HBr example I had before, it's a very reactive towards this reagent Br2, very reactive towards pi bonds. We have 2 pi bonds. We can reasonably expect it to go twice. But it is possible to stop it halfway. Requires some careful conditions, but it's possible to do it. Your book doesn't say a whole lot about that. I checked with a couple of other books. It can be stopped halfway if you're careful and use a little bit of other things in it. And if so, we might expect something like this, where we're now going to see a trans addition, where we end up with the two groups anti to each other, or trans to each other. Now, how did that happen? When we did this with an alkene, remember, we said that, we had kind of a question about this, whether this was sufficient to block one side, or whether we actually had to talk about the nucleophilic attack coming with that three-membered ring instead. So here is a good way of looking at it, because if there's a if there's not a cyclic intermediate here, we could expect to not be able to control this. We would expect the stereochemistry to be really bad if we don't have control here, because if we think about this, we'd be looking at something where, if we were talking about the non-cyclic version, we'd be looking at this, where we're looking at one bromine already in place, and out here, this carbon would still be sp hybridized, and we have a cation. There's absolutely no way that that bromine could control the approach of the other. Here we could debate it with the alkene case. We could debate that it's big enough to block one side and drive us to the other side, so that this cyclic intermediate is probably not as necessary. But we can't really make that argument for the alkyne, because the two carbons involved, one of the carbons is sp2, where the bromine actually has already been added. The other one is sp, so it's still linear. So we've got no way that bromine's going to affect this, unless we actually do have the cyclic intermediate. So here's what that would look like. If we did that, using the same mechanistic thinking that we used for the alkene, we'd start out with something like this, where we'd now have a bromine in place with its lone pairs, which I didn't draw on the original, and at least transiently a cation on the other carbon. If we looked at this forming a three-membered ring, which would clearly be very odd, then we'd be looking at this. It's still a cyclic bromonium intermediate, but it's incredibly strained version. When I was a student and I was taught this, it bothered me, because it just doesn't, we spend so much time talking about three-membered rings and how they're unfavorable and strained and blah, blah, blah. Now we're going to put an alkene in it. Really? So your book takes the approach of saying the mechanism of this is not really known. As it turns out, there are cyclopropenes. This is not an unreasonable structure. They are isolatable. They are stable enough to store them in some cases, which means that that intermediate bromonium ion's not quite as absurd as it might have seemed. Probably never going to be isolatable. The strain on it's going to be incredible, but not completely out of the realm of possibility based on just what can happen for carbons under the same circumstances. So, if that's the case, the second comes in, and we end up here with the complete or near complete stereo control. Now, the example that I looked up to actually have this is 3-hexyne. So, our alkyne has an alpha group on both sides. If we took care of this, now we're adding a couple things to this. Don't really worry about why. Just it's okay for the moment. It's just going to allow us to control things a little bit better. So we have a little bit of extra bromide ion by having the lithium bromide present, and if we're careful with that stoichiometrically, here's where we end up. We end up here with the ethyl group on each side, the bromines anti to each other, and this is 99%. It's 99% E. So, stereo control doesn't get much better than that. Now, under most circumstances, we wouldn't try to stop there, but the point is mechanistically that we can, and it tells us a little something about how the other reaction with the alkene probably did work, which is that three-membered ring is not a bad bet, and it's not even a bad bet here, despite how odd it feels, especially if you've ever tried to build a model of cyclopropane, then think about putting sp2 carbons in it. It would basically break the kit, so it's not something that we would normally think to be reasonable. But most of the time what we're going to see is this reaction done without any attempt to control it, so using an excess of bromine and undergoing the reaction twice. So we're going to be looking at basically a tetrabromide. So it's how we would get something like this, where we'd end up with 2 bromines on each of the carbons. Basically, same principles for the chlorination. The iodination is a little different. And whenever we talk about halogenation, just ignore the fact that fluorine exists, because most of the reactions with fluorine are a different world from what we see with the other halogens. So we don't bother with that in simple explanations, because neither does it. Most usefully, we're trying to put bromines in place most of the time because they give us building blocks for other functional groups. Chlorines sometimes, but they tend to work similarly, although the selectivity is not as good in some reactions. At least mechanistically, there's not a lot of difference between them, so it's okay to pretend that they're mostly the same, even if reaction-wise that's not entirely true when we displace them.